Hello, good afternoon, all. Let's wait for 2 to 3 more minutes and then we shall start the discussion. Am I audible? Hello.
Yeah, yes, Professor, you are well audible. Thank you.
Thank you. Thank you. Yes, the YouTube link I have shared. I haven't you received that email which shared the email means the YouTube link and the PDF that I have shared with NPTEL. Uh, haven't you received that link? Okay. Okay. Then I am sharing it here. Just wait. Mm, This is the YouTube link of the previous session, week one discussion. Okay, let's start for today and let others join. Yes, I think it's visible, right? So, similar to the last week, this week also we shall first have a brief overview. And I think the assignments are not released yet. Means what I think is that it will be released on 9th of August. So this week also we can't discuss the related assignments that has been given, but I have prepared something from the previous year's questions and as well as from some websites. So we shall discuss it later on. But till then, we will first have some brief overview of what has been discussed this week. So mainly the focus that was given this week was on the smart grid monitoring aspects like the smart grid elements where the RTUs and SCADA system were being discussed and also the some parts of smart meters and later on we are in the since we are learning smart grid so mainly distributed energy resources were being given the priorities means in this week with 4 lectures on distributed energy resources. So first of all, why do we need the smart grid monitoring and what are the main aim to properly monitor smart grids because is mainly we'll have to we'll have to make the proper monitoring because the smart grids are mainly it's quite intermittent since the presence of renewable is there so it's quite intermittent in nature. So we'll have to maintain systematic or the synchronization between the generation, because mainly since the renewables are main parts of the major uh, operating resources of the smart grid, where we have the let's start the recording. Yes. So since the main resources of smart grid is the renewable energy system. So from the renewable energy systems, we mainly try to focus on how to make the proper utility of those renewable energy sources, and based on that we need proper means we have two major part of the smart grid, where we have the sources like the wind as well as the solar power generation sources. So you'll have to smartly maintain or handle the resources so as to maintain the proper maintain the smart grid, or to operate the smart grid in proper manner. So first of all, based on that, we need smart grid monitoring, where we firstly SCADA system. So brief overview of SCADA system on was given last week also, but mainly what SCADA system aims to means for the smart grid operation, SCADA system aims to control means to have the proper operational features, means to maintain or to monitor the each and every operating principles of the. Yes, yes, please. Hello, hello. If any questions? Okay. Okay. So to have the proper monitoring of the smart grid system. So first of all, SCADA sys- we have the SCADA system, where there are the field devices connected to uh, each and every location. Means the field devices are connected. Yes, field devices are connected to the each and every equipments, and from these field devices, there are four to five types of systems. So first, here we have seen the real-time server. So it gives the proper real-time monitoring or tracking of the system. So mainly, what are the main goal of monitoring the system is that we need to monitor the states of the system. So what I mean is to say is that by the states of the system we have two parameters that are the base quantities, and based on that we can find out all the other derived quantities of the system. So mainly voltage, magnitude, and the phase angles, and their associated phase angles of each and every buses. So this is one of the primary objective, to find the magnitude and voltage angles of all the buses of the system. So this is the human machine interface, where the operators of the system, they work on, and they just try to monitor the each and every operational aspects. And what is the means after finding the state of the system, we can find out each and every other associated power flows and line power, branch power flows, the currents flowing through the branches, and all these things. So one thing is the real-time system when the server, where the real-time data is being processed. The other is the historical data server, but from the historical data server we can get the information of the previous week's information or monthly information. All these things are being stored. So from based on that, yes, the other one is the application server. So these are the applications server, where the means the what kind of operations need to be performed, that all these things are. So the applications what need to be performed. So based on that, we have the RTUs being present in the field, and these RTUs are known as remote terminal units. So here mainly we have the input output system where we can give input from the SCADA operating room to the RTUs, and based on that, they will perform the required operation, as well as based on the information that they extract from the field, these information are again fed to the operation room, so that the people working there they can get the real time picture of the power system or the real time picture of the smart grid system. So this is one objective of the input output system. Then is the data collection that I've already told. Other thing is that data processing means based on they first process the data, and after that they send the data to the master station, and also in some cases they need to perform data translation, and then they send the data to the master station. So various kinds of devices, RTUs are associated um, with the CTs and PTs, and in these near to these terminals, the RTUs are also being placed, so that these information, what are the information, what is the power flow, what are the from the RTUs we can also get the power bus power injections, power flows, all these things we can get, and these all throughout, if we constantly, as a part of state estimation, what we part of as a part of state estimation, we generally perform the state estimation where we need to have the, suppose we have a 15 bus system. So for the 15 bus system, we need to have at least 15 measurements, at least 15 measurements to make the system observable, right? So means to system observability criteria needs to be achieved first. So at least we will have to have 15 measurements from the RTU devices connected in the field. So based on that, we perform the state estimation where the data are being filtered and processed based on filtered and processed, and based on that they yield the proper operating voltage magnitudes and the associated phase angles of the system. Some bad data processing algorithms are also bad data processing algorithms. Yes, bad data processing, and something needs to be done, and based on that these there are kind of residual testing and all these things, and after that we find out the states of the system. So mainly smart grid monitoring is required from the based on the RTUs, and nowadays PMUs are also being micro PMUs in distribution level, since smart grid is mainly associated with the distribution level. So we have the micro PMUs in the distribution level where we can also monitor the states of the system, although it's too much costly, so we can't associate the entire this micro PMUs entirely into the system. So these are the main objectives of how the SCADA system, they take the information from the field, as well as they give the information as by with the help of this human machine interface, where the operator sits and they just gives the input to the into the computers or the operating systems, so that they deliver that same information to the RTUs, and after that these RT by digitally, and something digital analog converters are also present in the RTUs. and after that they process the operation that is being given by the operating operation room of the power plants or smart grid system nowadays. So this is the same thing that I've taken from the lecture. So here we can see this kind of operation, trip, close, open, starts, and all these things can be. This is master station, that means the operation room where the operators are giving the operation command. Operators are giving operation commands, and these kind of information they can be given to the RTUs, and RTUs can in return give the generate some analog. So uh, these RTUs deliver this output or control command, and something again to know the status of the system, like the data acquisition, some alarms or sequence of events. These status of these inputs are from the RTUs, to means from the this is the RTU part, and from these are the field devices. These are the field devices, field from the field. The RTUs are delivering this data to the so to the operation, and the operators can readily monitor the system conditions, so the system working states of the system. So this is a real-time processing algorithm. The state estimation that I have previously told in in the previous slide, what I have told is that state estimation is a regular algorithm which works on a real-time basis if required, and some necessary applications are being means there are two types, like the static and dynamic operation. Since power system is generally considered to be quasi-static in nature, or rather the smart grid system are nowadays becoming more dynamic. So this is conventional power system, and this is the smart grid system where the renewables are quite intermittent in nature. To monitor these states of the system, this smart grid architecture is this SCADA architecture or the PMU, some states of the system. The smart grid system, this real-time monitoring can be done through the SCADA devices, like the RTUs are mainly the remote terminal units that are mainly used to fetch the information from the field to the control center. And coming to the smart metering, so what the first one disadvantage of the distribution system? So disadvantage is that the these RTUs are, since in the distribution system we have constant means we have the metering devices like the energy meters and all these things in each and every residential apartments and all these things. So we what the researchers thought is that why not to take the advantage, why not to why not to fetch those informations directly so that they can be of some use, since in the distribution level the number of nodes, the nodes are quite high. Nodes are much higher than the transmission system. So since the number of nodes are much higher, so we what I have previously told is that we the each for each and every node we have a voltage magnitude and angle. So for all nodes, suppose we have 1,000 nodes, so we have 2,000 states. For 1,000 nodes, we have 2,000 states. Now, to monitor these 2,000 states, we need to have 2,000 measurements. We need to have 2,000 measurements at least. So, but in the distribution system, since smart grid architecture is mostly in the distribution, is related to the distribution level, so we can't. directly we don't have these many number of measuring devices or the monitoring devices which we can directly use from the which you can directly use to perform this smart grid monitoring. So in those cases, we generally use the previous forecasts of the data. We generally use forecasted load profiles, and all these things were generally done when these distribution estimation were being performed, distribution system state estimation. But with the evolution of this smart metering architecture, where previously what the people used to do is that they came to our houses and they used to take manual meter readings from our from the houses. So, but nowadays, since we have the smart metering architecture, where the meters can directly communicate directly to the control center, and what I have in the previous day, what I have also told that the DSO model has been proposed by the three research institutes like IIT Delhi, IIT Kanpur, and PERI, the Engineering Research Institute. So since DSO model is proposed and we are means driving towards this DSO model, so why not to take the advantage from the smart meters? These smart meters have the data, but as per the rules that government has proposed that we can't directly take the smart meter data. What we can do is that we can get the information of the aggregated smart meter data. And to take the aggregated smart meter data in the distribution nodes of the distribution node of the transformer, means the nodes that we here we have considered. So we can aggregate that data so that the data aggregation procedure is generally followed, because to render the customers from getting the these kind of theft activities, to prevent the customers from these theft activities and all these things. So we generally use the aggregated smart meter data. So this smart meter has the signal acquisition block. So what is the signal acquisition block? This takes the information, this collects the data from the system, and after that signal conditioning, where we perform this signal conditioning so that we only allow the fundamental component to the measurement of the fundamental component is required. So for that, we need to perform some signal conditioning activities, and after that, the analog to digital conversion is done, and based on that, the communication, and after that, the data is being communicated to the system, communicated to the control center, right? So this is the main procedure of how the smart metering architecture works, and the advantage is that since previously we used the forecasted load profile, so the forecasted load profile had uncertainties of this forecasted load profile were much higher than the associated smart meter data. Means whenever we perform this state estimation activities, so based on state estimation, we have these means based on data, all the metering equipments are not ideal. So since the metering equipments are not ideal, so we need to filter those metering equipments. Otherwise, we could have directly used the measurements and we could have directly told that this is the state of the system or the state of the system. But we can't do that since but the main basic objective is that we need to find out the states of the system, but we can't directly use the measurements because their measurements are having the mixture of real knowledge of data as well as some associated errors, knowledge of knowledge of the, let's call it, of the working state, plus uh, some errors. These errors are mainly the metering errors, as well as these errors can be considered as the system errors, system dynamic errors. But whenever we consider, suppose these are the with the metering errors are quite low. Since we don't have much information, since we don't have the don't have much information of the much information of the system. So what we do is that we use the forecasted load uh, load forecast profile as the measurements, because we don't have in the distribution level, and smart grid is mainly concentrated in the distribution level with large number of renewable things, renewable energy resources. Since smart grid has large number of renewable energy sources, so in this scenario, the forecast that we generally use consists of, since this forecast is considered as measurements, as because we don't have total number of measurements, but we still need to have the number of measurements more than the number of states of the system. So what we do is that we use the forecasts as the measurements with higher error associated with high uncertainties. Now, whenever we consider these high uncertainties, then we are deteriorating the effect of the estimation. So we can't monitor the system properly. Means with higher errors. So the estimation error was previously high. Now with the smart grid architecture, now with the smart metering architecture, what we have leveraged is that smart meters, what we have done is that aggregated data can be taken, and these aggregated data can be used on a real-time basis to monitor the system to make the measurement vector redundant in nature, and hence this estimation improves of the distribution system. This is one objective, since although these meters are also having some errors, but these errors are much less than the uncertainty of the forecast. So uncertainty, these errors are much lesser than the uncertainty of the forecast. So this is the main goal of or objective of why the smart grid monitoring needs to be properly done. Okay. So any questions related to this part? Okay. Am I audible, right?
Yeah, Professor, you are audible.
Okay.
There's no
Thank you.
questions.
Thank you,
Thank you,
sir.
sir.
Thank you. So, uh, so that ends up the smart grid. What is it? Smart grid monitoring aspect. So now coming to the smart grid resources, distributed energy resources. This is the diagram taken from the lecture slides, lecture notes. So mainly we have two types of the residential part and the commercial part, and all the distributed energy resources. We have the distributed energy resources. So yes, so we have the distributed energy resources. So how can these distributed energy resources being is we need to have mainly the spread of the smart grid architecture is quite high. So everywhere we can install this solar photovoltaic or wind system, natural gas fired, and all these things, battery banks, and all these things. So we have the resources. So since we have each and every household have their rooftop, so they can install these solar photovoltaic resources, and solar photovoltaic or any small kind of wind farms can be which wind farm can be established on or on their fields, where if there is any high density of wind. So all these things, entire thing is there in many of the states in India. There are some protocols that if the generation of each of these household exceeds, suppose 1 kilowatt of 1 kilowatt generation exceeds 1 kilowatt, then they can feed the grid. So So these are some of the kind of distributed energy resources from the residential sectors, and these are the from the commercial and industrial sectors. Then biomass components and all these things, fuel cells. These fuel cells are mainly hydrogen powered fuel cells. They take input as these fuel cells takes the input uh, as the hydrogen, and yes, gives output as the uh, water vapor. So hydrogen or oxygen, and finally, I think they exert the water vapor. So these all these things, fuel cells are also getting means day by day they are also getting quite quite a stable position, because the electric vehicles, in place of electric vehicles, the fuel cell vehicles are also under the process. So these are the now another thing is that in the electric vehicle case, the why the distributed energy resources are distributed means the term distributed is justified, because the since all these customers are we have become prosumers, where they can produce as well as consume. And also suppose some electric vehicle owner have they will be going somewhere some any places. So in those cases, if they think that they can feed the excess electric vehicle the battery energy stored in the battery of the vehicle. So these V2G, vehicle to grid mode, and all these things are quite coming up. V2G mode and G2B. G2B is there, but V2G is under the Indian scenario. I don't think this has already been. This is mainly under research with V2G, and the combined CHP plants, where we can deliver both the power as well as the heat. Well, this heat can be for the cold regions where the temperature is quite low. So in those places, these power heat, combined heat and power, means this heat energy is being transferred to these households to maintain their temperature, means to maintain their room temperature constant. So mainly what we from the distributed energy resources. So previously in the previous week what we discussed is that around 16% of total generation of India's total generation is solar photovoltaic, and around 10 to 11% of the India's generation is from the coming from the wind. So this is around from the out of total 410 gigawatt. So if the 16% is quite a good number, good percent, good value. So this around 26 to 27% of the total energy is being obtained from the solar and wind only, although we have the other renewable resources, but still. So we need to harness this solar and wind energy in much better way, so as to meet the nation's objective, that is by 2030 we need to have 50 watt. Government Ministry of Climate Change has proposed is that by 2030 50% of total energy consumption should be from the renewable energy resources, and the remaining by 2070 it would follow net zero condition, net zero as carbon to reduce the carbon footprint. So so for that, considering these scenarios, distributed energy resources are means they are distributed or scattered in such a manner, but still they need to perform or to maintain the same frequency if they are synchronized with the grid. This is the main objective why this smart grid thing needs to be taken well. Is the control and design of these equipments and all these things of the smarter to maintain the smarter power and all these things. So for smart grid monitoring, as well as each and every individual, mainly like the solar. For this week lecture we have mainly focused on the solar and the wind resources. So let's start with the solar energy system. And so in the lecture slides, also lecture notes, videos, you have also seen that this is the solar cell, and with the solar cell, the modules are developed, and when modules are clustered together, they form panel, and large number of panel forms array. So this is the main objective of the solar energy system, which is static in nature. And another thing is that what is the drawback of these static solar energy system, since it's giving around 16%, 16 to 17% of total power. So what is the issue what India is facing, or the other countries? Let's keep aside. What India is facing is that the the smart grid system is, we are aiming towards the smart grid system, but the coal based plants, those plants they had the rotating masses. So the rotating masses delivered the required inertia of the system to maintain the frequency constant. The inertia of those systems helped in the operation of this maintain the frequency of the system. These rotating masses aided a lot, because suppose we have sudden decrement in load, and this entire sudden decrement is load is being coped up by the synchronous generator inertia, rotational inertia. So it won't allow to suddenly fall, means let the frequency down. If load decreases, frequency increases. So it won't allow the speed to fall down suddenly, and thus thereby maintaining the frequency, means at least try to maintain the frequency constant. But in the renewable resources, the solar, I mean, especially the solar part, they don't have this kind of inertia and all, the inertia. So what drawback is being faced is that the for this intermittent load changes, and what solar is that we need to obey what the means obey mainly the meteorological data, mainly focus on the meteorological aspects of data, and based on their data we need to monitor, or we need to means take as much amount of generation as been given by the solar energy system. So these unit commitment problems and all these things, in those unit commitment problems, what previously, when there was no solar energy system, this solar energy and these renewable, no, if there, when there was no renewable energy resources, when only the thermal power plant based operations were being performed, the unit commitment or the economic load dispatch after those, the only around 5 to 7% of the generations were being kept as spinning reserve. Only this much of spinning reserve were enough, because the entire generation or the control is on the hand of the operators, or the means the control operation, means the NLDC, the operational executives, they had the entire authority of how they will be controlling the solar and not solar, sorry, the thermal power plants, when the most of the generation were from the thermal power plants. So 5% of spinning reserve was enough. But since the solar energy system or the wind, these are intermittent in nature, so we don't have that amount of certainty in our prediction, because since we are not predicting the meteorological data, weather forecast is itself, the term forecast is being used, which itself is allowing a term called uncertainty with same. So when this uncertainty is being associated, so in those cases, as the rotational masses are not there, so system inertia needs to be prevailed, because system inertia, if there is not that amount of system inertia, not enough amount of system inertia, so in those cases the frequency fall. And although we need to one grid, one nation, one frequency, so we need to maintain the system frequency constant, and various power plants gets the APT, availability based tariffs, and all these things based on how they maintain the system frequency. So in Indian scenario, this virtual inertia development is being with the help of these power electronic converters and all these things. Virtual inertia is being worked on. Means this is under research progress, and this is not entirely up to the mark. So 5% to 6% spinning reserve got now around we require around 20%, 18 to 20% of the total, around. So around 18 to 20% of uncertainty to meet the 18 to 20% of spinning reserve to meet the uncertainty. 18 to 20% of the spinning reserve are being kept so that these kind of fluctuations and all these things can be trade off. So the large number of, so what is being incorporated into, since we are aiming towards smart grid, but we need to minimize the cost also. But in these circumstances, cost is not getting minimized. So this is the one drawback of how Indian scenario, and it's under the working phase, so might be we would be getting some positive results in the coming days. So here the solar energy system, it is the PV panels, and based on the PV panels, we have the energy inversion and conditioning block. It is required because these energy are getting directly from the PV panels, but this energy inversion, since this energy is DC, PV is generating in DC. So what we have to do is that it is not a constant; it's variable in nature. So for we can directly convert, if DC is converted to converter, and all these inversion performances are being done so as to convert in it into AC part, as well as the the control action means to maintain a steady kind of steady power flow. This is being performed, and although this the DC energy, we can directly store it to the batteries, and they can be later on used for the future objectives to in scenarios when there is no DC power, right? No supply from the solar means in the during the night times. This battery energy can be utilized for the other usages. So this is the grid connected mode and the off grid mode. The grid connected mode and off grid mode. We have these both diagrams. These are being in the discussed in the lecture only. So here the direct connection is from the rooftop of the solar to the substation and to the grid. Means they directly supply to the grid. They feed directly to the grid. What I've told previously is that around, if in some places, if we have around 20 around 1 kilowatt of power generated from the household resources, household 1 kilowatt, then they can, from the household or residential apartments, they can feed directly to the grid, and based on that they can use the net metering and all these things, right? So, and the off-grid mode is that they are connected, means they are separated from the grid, and based on that they are operating with the battery bank and all these. They have the battery bank which would be used for later usages, and the charge controller, they maintain the proper, means to feed the loads, the how much or how to utilize these or how to control these energy, and based on the controlling action, these charge controller would feed the, based on the requirements, they would feed the power to the loads. So these are two kinds of grid mode and grid connected or off grid mode operation. So this is the block diagram. It's again from the lecture itself. So here we have the PV array, and from the PV array, there we have the inverter or power conditioner. So it is converting the DC to AC, and from the AC it is being fed to the distributed panel to the AC loads and utility. And for the other part of it, for the off-grid mode, the charge controller is present, which is storing the energy in the battery, and they are also, it can also feed the direct DC to the DC loads, and battery can invert it to AC, and they can feed the AC loads. This is, these are the basic block diagrams of. what is the main basic block diagram of the solar PV operation. And yes, so any questions? So so coming to the PV system modeling, is the solar PV modeling. Here we have the two types of resistances, shunt resistance and series resistances. And the shunt resistance, so what are the aspects means why the shunt resistance needs to be modeled in the system? These are the main things that there are system manufacturing defects and poor cell design. And so for to meet the objective means to design the proper means to minimize, what we need to do is that the more and more amount of current should flow to the load side. This is the objective output. But if we have this shunt resistance, so if this resistance we will have to, the main agenda is to have more power on the output side. But if we have this shunt resistance, this current drops to a larger extent. There we have the series resistor also, where the current drops so that the voltage gets lowered. This thing needs to be controlled because we need to minimize the emitter base resistance, because the series resistance part is being mainly due to the effect of emitter base resistance and metal contacts with the silicon, and also with the metal contacts of the top and rear parts of the silicon cell. And for this shunt part, perfect design objectives needs to be met. And for the series register part, these things needs to be taken care of, because the more and more amount of power needs to be extracted, rather than the, because since the efficiency of the solar panels or the solar cells are quite less, means around, the solar PV system is around 15 to 16% of the total PV system. So these are the two modeling aspects, and based on the modeling aspects, what we can observe is that this is the main working equations. And in some cases or the other, if we have in some cases, if we have these the series resistance values, the shunt resistance value should be higher, the so that mainly the device means the current mostly flows through the towards the outer side, means towards the load side. So in most of the cases, this RSA in ideal cases should be very high than that of RS. So these equations gets modified accordingly, and these are some of the parameters. And this is the PV characteristics. So what does this PV characteristics imply is that we have this block, the block is the maximum power that can be extracted. So mainly the PVs work on the MPPT system, is the maximum power point tracking system. So here what we can observe is that this is the PV curve, and this is the maximum current, and this is the maximum voltage. And based on this maximum current and maximum voltage, we This is this is the maximum rate, yes. So this amount of maximum power that can be extracted is given by the maximum current Imax into Pmax. Sorry, Imax into Pmax. And we have the short circuit current where the voltage is zero And when this is the short circuit current, where we have the voltage is zero, and here we have voltage VSC is equal to zero, and here we have the open circuit voltage, that means short circuit current ISC. ISC when short circuit, sorry, this is uh, this is VOC maximum. VOC VOC maximum means yes, current is zero. This one is short circuit current, not VOSC. This will be VOC. That is open circuit voltage should be zero, and this is short circuit current means this is VOC. ISC. Okay, no. ISC, it means the system is short circuited. So voltage will be zero, not VOC, and here it will be the current will be zero. So here the current will be zero. So based on that, we mainly find out the fill factor of the system. So what does this fill factor imply is that we have the power output, and here it will be the power output, that is maximum, the power output maximum, and here we'll have the OC and ISC. So what we can observe is that the output power is VMP and IMP. So this one is IMP and this one is VMP. So IMP and VMP, these values are lower means than that of VOC and ISC. This one is ISC, this one is ISC, and this is IMP. So these values are quite lower, and similar to this case, this is VMP. So what we can observe is that the VMP and these fill factor values are greater than that of the numerator is lower than that of the denominator. So numerator here it is generally less than one. The fill factor value is less than one, and the ideal value should be one, but it's always generally less than one. Ideal value should be one, but it's generally around point 0.8 or point 0.7 like that. So here we can observe what is this is the PV characteristics, and we need to operate in this is the PV power curve. So what we observe is that the maximum power point needs to be tracked, and the solar panels or the PV system should be operated in this like MPPT condition, means the maximum power point condition, so that to derive the maximum power from the operating out from the solar energy system. So as we require, as we can derive the maximum power from the solar. So if we can derive the maximum power from the solar equipments, and one more thing is that these solar, the weather and all the sunshine, the irradiance is constantly varying. So as the irradiance is constantly varying, so we can't even expect to have the constant this power profile maintained. So each and every time these controllers are designed so as to maintain the MPPT, so as to track the maximum power point, and in those operating scenarios, the power equipments, these the solar power panels would deliver the maximum possible power in such scenarios. Okay, and it is a variable condition. So the power point tracking needs to be performed on real-time basis as per the variation in the solar irradiances. So here it is all about the characteristics. Now coming to the series parallel operations, coming to the series parallel operation. So what we can observe is that if suppose we connect a large number of the solar PVs in a series, so what does what does the series combination give? Is the series combination in normal, if suppose normal series circuits and parallel circuits, if we consider the series circuits would be giving the series circuit would be giving the yielding higher voltages. Means if we have this, these series circuits would be yielding higher voltages. It's a general analogous thing what I'm trying to tell. And the when we have large number of parallel sources, these are not sources, sorry. I should have drawn some sources. So yes. So if what we will get as an output, if we measure it using a voltmeter here, we will be getting the sum of the two voltages. So whenever the solar panels and solar arrays are connected in series, so that will be yielding the higher voltages. That will be giving higher voltages. And whenever we are operating in parallel position, means suppose we have the sources in parallel, suppose we have the current sources in parallel, all these current sources would be, if we measure through a resistance, all these would be delivering the sum of the I1, I2 and I3. All these sources would be delivering the sum of I1, I2 and I3 with if we measure it as a with an ammeter here through a resistance, we can get the sum of the currents here. So this is the main objective, and to make this analogous application here, the series and parallel operation of the solar PV panels and all these PV panels or PV arrays are maintained, where we can find out the more amount of is the in both the cases the power output is being obtained. So in the power output, this is the V and I. In the parallel connection, current is increasing, voltage is constant, nearly constant. The maximum power point is constant, but here the maximum power point, not maximum, the voltage is maintained constant nearly. But in these cases, the current is constant, but the voltage gets increased to twice, or based on the number of arrays connected. So coming to the how irradiance would deliver, means how the various kind of varying irradiances would deliver results in the output characteristics of the system. So in those cases we have the IV curve of the PV array. So what we can observe is that suppose we have uh, this is the irradiances 400, 600, 800 and 1000. So based on the irradiances, the the MPPT values are also based on the irradiances. These values are getting the power output is getting enhanced. Initially, it was operating here, then it went here. So what we can observe is that based on the irradiances, the power output is getting enhanced. So that we can also understand that more the amount of solar irradiances, the larger number of the electrons. This is the means the main way. So with more amount of irradiance, the electron density would be higher, and since the electron density would be higher, the short circuit the current value will be increased, and hence we will getting the higher MPPT or the higher maximum power point as per the requirement. So yes, so this is all about the solar PV system. So any that is anything. So this is all about the solar energy system. Now coming to the wind energy system. So mainly wind energy is delivering around 10 to 11% of the total energy demand of India. So we have two types of wind energy system, like the offshore and the onshore. The offshore, what is the objective of keeping the offshore wind farms is that the air is higher in the midst of the oceans, so or the water bodies. So we need to have a constant air to circulate. So for those cases, the offshore wind is required, and the onshore wind is also present, but mostly people try to place the wind energy sources which are part of distributed energy resources in the places or the offshore areas. So this is mainly the issue. So we need to select proper sites for the wind farms or wind energy systems, because based on the choice of the or the choice or the area selection, the wind energy means harnessing the wind energy can be enhanced or enriched, because the if we select it in some if we place these wind farms in areas with lesser amount of wind circulation, hilly areas, and in the in it's kind of not in the flatter plains and the ups and downs, more ups and downs here and there. So in those cases, the wind farms can produce the maximum power that needs to be generated. So these wind farms also work on the principle of maximum power point, and what we can see is that the wind farms are generating first, and with the help of the cables, these are from the from the offshore substation we have, or we have onshore substation, and based on the offshore and onshore substation, we we take the power from the wind power is mainly AC in nature, and from this onshore and offshore substations, we deliver the power to the transmission lines and to the residential or the loads and all these things, the same power transmission phenomena. But for the time being, we can consider the case that the wind energy system, but whatever we generate from the wind energy system, these the placement of these wind farms is a quite a tedious task, as because it is mainly located in the coastal regions. So based on the distances or the coastal regions, these wind farms uh, these wind farms require a large amount of kind of the transport cost and all these things. And once these transport costs are means once these wind farms are established, these wind farms, or let me just with with large amount of wind farms, large. amount of wind power generation from the distant locations. What is the issue is that high amount of transportation cost before establishing the wind farm. Transportation cost is being invest larger cost or investment high investment before establishing the wind farm, and later on when the wind farm after it has now it is post installation a large amount of transmission cost is associated. So whenever we have large amount of transmission cost, so mainly from the perspective of DERs, mainly from the perspective of DERs, what we generally try to do is that suppose here we have the load center, load center. So we generally try to restrict our the wind energy or the solar energy, all these things. We generally try to keep the transmission cost minimum. So in these cases, in these uh, we need to generally try to minimize the transmission cost. But in the case of wind, so we need another transmission cost, and these transmission cost needs to be considered as a part of the smart grid feature or smart grid enhancement. So we need to minimize the cost after all. So everything needs to be chosen optimally. So site selection for wind farm is a quite hectic task. And here and two types of generally wind farms are seen uh, mainly wind turbines that we call is that they are of mainly two types. Means one is horizontally mounted, horizontally horizontal axis, or horizontally mounted and vertically mounted. Means they both have the axis. So axis mainly the for these vertically mounted, they have the axis horizontal, and for the horizontally mounted, they have the axis vertical. Means there we have the and all these where the wind blocks and all these things to keep. They would be constantly rotating in a clockwise or anti-clockwise direction. And here in the case for wind turbines, these are vertically mounted. They will be also be operating in a similar fashion. So the speed, what we can see, it is the hub, and the main bearing is there. And after that, we have the main shaft. So what is just wind speed is generally around 15, 10 to 15, 10 to 10 max to max means 15, but we around 7 to 8 meters per second, 10 meters per second. So in these here we will have the main these blades of these blades will be placed in this region, and the blades will be rotating based on the blades. We have the main shaft. The main shaft will rotate with the in the same speed as that of the blades of the wind turbine. And what we observe is that this is the main shaft. This is the shaft connected to the gearbox. Here the gearbox will be enhancing or the will be multiplying. The factor will of the gearbox will be there, which would enhance the speed of the means the rotational speed, which is very slow, to the generator speed that is required, because these generators are mainly induction generators. So they need to operate in a sleep speed, but the sleep speed can't be this much, 15. These what we see at a very slow speed. So these gearbox are generally given to enhance the speed of the system. And here we can observe the other shaft of the main shaft of the induction generator. So or the induction generator, and this is the thing is suppose and it is the called it is the brake, because brake is also required because we need to maintain the speed to the as per the requirement of the generator, as per the specifications and all these things. We can't drive these system much higher or much lower than that of the uh, specified value. So to maintain the constant, because wind is not on the wind is not controllable from the human or the operator's side. So what is controllable is that uh, the brakes, these braking system, this is a constant, this is a closed loop system. It works in a closed loop manner. So whenever the speed exceeds or there is speed exceeds some levels, so some specified level, the brakes would actuate, and these brakes will be mainly working is mainly limiting the speed of the induction generator. And this is the main operating principle. What we can see if this is the wind here it is mounted. This entire system it is mounted inside this. The entire system is mounted here, and this we can see. This is the basic block diagram where we can see that there is no controlling action, no controlling action, and whatever it is being generated. And another thing is that the the pitch control is there. Here we need to perform the pitch control so that the angle pitch means the blade and the axis of the blade and the main axis of the blade and the blade axis means this angle is the pitch angle. So we need to control the pitch angle based on the wind direction, and we have the at last at last we have the vanes, wind vanes and all these things. So based on these wind vanes and anemometer, we get the information of uh, how the wind direction, what way the in which direction is wind blowing, and based on that we can have the speech control, and so that the proper orientation can be done and the maximum output can be taken from the wind turbine. Means maximum generation can be made possible from the wind turbine. So here we have the gearbox. So this is the same gearbox, and this is the wind turbine with variable pitch blades. Okay, the blade speed means blade speed can be varied, but one issue is that after the gearbox, when it is a synchronous generator, so the AC power is what we get is not a varying frequency. This is a fixed frequency, and it needs to be always controlled, always being operated at the same speed. So since the synchronous generator has this kind of means the poles gets locked to each other. So whenever the speed of these wind is higher or lower, so if they try to force it against these locking, so in those cases the any kind of means the damage can occur in the generators itself. So this is mainly the operating principle of the wind farms of the thing of the fixed speed variable pitch blades method of the very fixed speed variable pitch blades. So okay, okay, this one. So we have the variable frequency operation as well. So what we can see is that here, based on the speeds of the wind, is how the wind will hit the blades, and we have the similar gearbox. These are the fixed pitch blades. We have the gearbox. This gearbox also have the same fundamental function that they need to properly maintain this gearbox need to be properly enhancing the speed, enhancing the low speed operation, low speed wind operation to the machine level. Okay, so here we have these variable generator. This is a variable generator. This variable generator is synchronized to the turbine speed. Means this is a variable generator. Although we have this variable frequency, this based on the variable frequency, wind is in varying nature. Wind is varying in nature. So based on the variable wind speed, the gearbox is also means in the secondary side of the gearbox, it is also generating a variable speed to the synchronous generator, and based on that variable speed, these uh, based on the variable speed, what we can observe is that the See, the frequency is also variable, but we can't operate in a variable frequency because the output side we have the loads and all these things connected. So they require the same frequency to operate. So to perform the same frequency operation, what we can do is that we associate these AC-DC converters and the frequency converters. Firstly, the AC is converted to DC, and after that the filtering action is there to filter the unwanted ripples and all these things, and after that DC is again inverted to AC. So when the DC is inverted to AC, the this becomes control level in nature. Okay, so this becomes controllable in nature, and based on this controllable action, we can maintain the steady frequency in the output side of the system, right? So from the amount of the means to here we have the speed pitch control, but this part is fixed plate. This operational control can be also incorporated based on the feedback closed loop feedback path. So here it is the kind of variable speed, fixed pitch blades, and this is kind of the another block diagram of the asynchronous generator. Here directly the variable voltage and variable frequency that I have told it before, these operations can be performed, and we have the rectifier unit which after the voltage regulation, the rectifier unit is being fitting to the DC control unit. Okay, and this DC control unit is feeding the battery, and from the DC control, suppose we have some DC load to deliver, so we can directly deliver the DC loads to the deliver the DC loads directly, DC load directly, and in the case of AC, this is the DC control. Surplus energy can be stored to the battery, and the DC control unit can be stored to the can be used for DC control from the DC control or sorry from the DC control unit we have the inverter, and from the battery also we can convert the DC to AC, and the AC power loads can be fed. Okay, so this is the main working or fundamental working of these variable pitch these blades and all. And these now it is the wind power characteristics. So what is the wind power characteristic? So we can observe is that here also we need to operate at the rated speed, so that the maximum power point tracking can be performed. Like MPPT needs to be, this is a real time process where the power point tracker constantly monitors the maximum power point, and based on the maximum power point, the wind power system would be delivering the required output. So this is the cut-in speed. This is the cut-off speed, sorry, and this is the cut-in speed. So this is the minimum speed at which the wind turbine should operate, and this is the maximum speed after which the wind turbine can't operate. Okay, so this is the overall characteristics of wind power characteristics. And now coming to the India's installed capacity, these are data I have taken from Wikipedia. So what it has been observed is that from the financial year, so as we are going towards or moving towards this renewable energy thing, so renewable energy aspect or renewable energy scenario, so we are enhancing the proper monitoring, means enhancing the renewable energy resources when the power outputs are being enhanced or increased to much higher level for the solar also, solar, wind, and mainly this is for the wind because the wind energy, what we can observe is that gradual increase means every year there has been a gradual increase, and now it is around 42, 42, yes, it's around 42 megawatt installed capacity. Installed capacity in megawatt, it's given around 42.42, sorry, 42 gigawatt, sorry, not megawatt, sorry, around 42 gigawatt we have in our presence. So this thing needs to be finalized to around, means by 2030 we need to achieve the 50% renewable part. So 50% around 410 gigawatt is our net power demand. So out of this 410 we have around 16% to 17% solar, and around 10 to 11% wind. And another what ministry says, they said that now the new Ministry of New and Renewable Energy, this energy resource, this ministry mainly incorporates the solar, wind, and the hydro. Hydro is also a part of this MNRE. So since hydro is a part of MNRE, so what we can observe is that the hydropower is around 10% of the, another 10% of hydropower can be generated. Hydropower generation can be considered as a part of the total renewable energy, that is around 50% by 2030. So this is the main overview of the wind energy system, and all these things. This why the requirement of this smart grid monitoring came into picture is that this, let's suppose this solar, wind, everything, all these are mainly highly intermittent in nature, highly intermittent, and due to this high intermittency, the solar, wind, and all these things, they need the, now we'll have to deliver the requirement of load. The required load needs to be delivered. Now, how this required load? So for that we need to have optimal scheduling. Now, since the previous optimal scheduling, previous optimal schedulings and all these things, they were mainly were a part of the, which they consisted of the thermal power plants which previously needed to be optimally scheduled. But coming to these real time scenario where the forecast changes, and based on that this RTM, have you heard of the name RTMs? So okay, that means RTM means the real time markets. Okay, so previously it was kind of DAM. DAM means day ahead markets, but nowadays it's being considered as a real-time market. So for that, if every 15 minutes lap, by every 15 minutes lap, forecasting needs to be performed and real-time forecasting information needs to be delivered. And we also have these two now the market come whenever the term market comes, we have these two, this Indian Energy Exchange IEX and Power Exchange, yes, Corporation of PXL, Power Exchange of India Limited, something like it. These two are market which real time they take into consideration for all the market strategies and bidding, where the private entities as well as the private entities as well as the uh, public entities can public entities can can keep the stake, some part of the generation or some part of their all these things, the generation mainly some part of their generation, so that they can participate publicly in these Indian energy in these market activities. And based on these market activities, what we can observe is that the dynamic as behavior is highly pronounced. So for these purposes, smart grid monitoring, what I previously discussed, that why it is the need of smart grid monitoring. This estimation, mainly the state estimation thing, the optimal power flow, the scheduling, the power flow behavior, power flow characteristics, and all these things. How these things can, uh, how these things denote uh, much. So how these things can be considered now, with the loads being much higher than the generation, than the transmission level, because transmission system is quite highly enhanced, and their characteristics, their features are quite highly enhanced, so pronounced. So in pertaining to such scenarios, the distribution system needs to be monitored in the context of smart grid. So So this is the main overview. Any queries, any doubts, or anything like anything that you want to ask, any these things you can do. So this is the mainly this week's overview, and we can just the solar part, the wind part, and as well as the real-time monitoring, the smart grid elements of smart grid monitoring. We can observe the assignments. Will be released. So on the next week we can discuss the first two assignments. But till then we can't do that. So I've prepared some questions which I will be discussing. Which I firstly few people can participate. Few people should participate because I have prepared these questions. These are mainly the objective type questions from the previous year uh, question banks, these things, previous NPTEL banks. So you can participate. So if you have any queries, please ask. Hmm. And one thing is that here we can control is this the controlling action. We can control the voltage, power factor, and all these things. And based on we need to control the voltage power factor, and based on the voltage and power factor, we can associate means we can find out the proper operating means we can control what is required from the. Yes, sure. uh, I'll share this ppt, and I think you are getting the you haven't yet received any link for where you are getting this. I have already uploaded and shared with the NPTEL site. I think they will be sharing. I can't directly share it here because you will get the link because it is been previously told that you will have the access to these links, this to these PPTs and the lecture videos. So I have already shared the we have other TAs also shared, and I think within 1 or 2 days, maybe you would be getting. And this PPT I will definitely share in the upload section. I have uploaded in the previous weeks, but this week PPT I will definitely upload and share with all of you. So you can access as per your convenience, and since all these courses are registered by large number of candidates, so many can't join in each and every session. So you can access from YouTube. So let's start with some of the MCQs that I have prepared. So you can please participate, and it would be good. Otherwise, I need to. And I think these questions are visible, right? Yes. One. One is real-time server. Okay, front-end real-time server is okay. So any other options? I'll say front-end processor. If it is an interface, front-end processor means the operation system, the operation um, personals room is the control substation or the control station. They work on Yes, they work on real-time data, but yes, operation. This is also a part of the answer. Uh, yes, yes. So all of the above is the correct answer because the real-time data server, all these things is the real-time data server, historical data server, and operation workstations. Means the front-end processors interact with all these three because in the monitoring aspects I told previously that they RTUs on the SCADA system work with the constant real-time data surveillance for the real-time monitoring of the system as we are aiming for the smart grid this real-time system and all these things real-time data real-time monitoring dynamic. Now historical is that because suppose we have in some cases, suppose what I have told previously, the state estimation objective, right? So, in the state estimation objective, it is considered this one case. So, based on the state estimation objective, what we require is that we require the voltage magnitudes and phase angles of all the nodes, right? Or the buses. So, suppose we have the in the distribution scenario, in the distribution scenario, what we see is that the number of measurements, since the measuring equipments, measuring devices are quite less, and due to these reasons, the distribution system measurements are somewhat being corresponded with the other with the historical load profiles, and these load profiles are being as considered as measurements, because due to the lack of data, and we have to have this means we'll have to meet the objective of system redundancy, which means the number of what is the measurements should be greater than equal to number of states. At least it should be equal to the number of states. So in such scenarios, measurements aren't there. The real-time measurements aren't there in the system. So the operation thing needs to be done, because this is the primary objective. This is the objective that needs to be made. So in those cases, the historical load profile data of the nodes, which is again obtained from the smart meters, previous smart meter data that have been kept. So those smart meter data, historical data, can be utilized, or the forecasted profiles or the previous load, means maybe of the smart meters, might not be of the smart meters, means if considering the previous systems fail, it take historical data. Yes, it is also, if some RTUs fail, it also takes the historical data. That is also one of the correct points. And sometimes we also take the, there are some instances considering some real-time applications. Suppose we have some measurements didn't arrive, means sensor failure. So we then consider the various interpolation techniques based on the historical trends and all these things. We incorporate these historical data and all these things to perform the real-time state estimation of the system. So historical data server is required to work on the, is the real-time front-end processor interface with the historical data at large. Okay. Yes. To what is the function of data translation application DTA? अच्छा, mm, presents data to the master station. Data translation. Yes, it they sends data to the master station, but before that it performs something. Means data translation, they transfer the data to the master station as per their requirement. So means you are partially correct, but this answer is something different. Yes, no, acquires data is not correct. Acquires data is not correct. Else it acquires data is being acquired, and after that this data translation application part comes into picture. Means they mainly uh, they mainly find out these kind of various analog activities like the missing data, bad data. To detect those data, they just send the manipulates. This is the correct answer. They manipulate the data before they are presented to the master station. Yes, yes. After some manipulations, right? That is yes. Two A is the correct answer. So this is the main. So when moving on to the next question, third one. 3-1. No, not one. Any other? Any other? No, not 3D. It was during the lecture by Professor Premlata. So she directly told this value in the lecture. Anything else? Not 1 and D. Means 1 and 4. So answer is in between 2 and 3. So this answer is 57. Right? This is 57% of the PV array of the system overall cost is 57% is for the array, right? And 30% is for the 30% is for the control actions, the storage and all these things, control design and all these things. 30%, and only yes, please, please. 4D. Uh, no, not 4D. Series resistance. Series resistance. What does the series resistance do? Series resistance, it decreases the output voltage, means this voltage drop VD VD increases if series resistance is by controlling the series resistance value. And what is field factor? It is Vmax by Imax, Vmax Imax by uh, VOC ISC, VSC ISC. So what is the main implication of this V series resistance drop is that with the help of this series resistance drop, so we can control the V output. So these output voltage can be controlled. So what we can control is that the open circuit voltage is 4D. No, it is 4C. It is fill factor. Mainly, it reduces the fill factor. Where our main objective is to maintain the two, means our main objective is to fulfill the fill factor value as 1, to obtain the fill factor value as 1. But in general case, yes, for C is correct. But for fill factor value, the main impact is on the fill factor. It can't be increased beyond 1, so it gets reduced based on the impact of the series resistance, right? Significance of fill factor, it implies that how much fill factor would give that, since these Vmax and Imax are the maximum allowed values of the system. So if we can operate this Vmax and Imax, means the MPPT, we need to operate the system at MPPT, maximum power point tracking. So if to achieve the maximum power point, we need to achieve this Vmax and Imax to the highest value, means the maximum value, V and I to maximum value. So fill factor indicates how much we are attaining the, means how much we are attaining the, means the power that we can fetch from the system, means that we can obtain from the solar energy, solar PV system. So how much maximum power can we extract from this PV system? That is the, that measure is can be, that is the main significance of this field factor. We can get a measure, we can measure the, means the scale, the value, how much it is nearing to the maximum value. Since it can't, it has to operate in a maximum power point mode, maximum power point MPP tracking. So fill factor gives the information how much we are close to the one value. One is the best value, so one we can't achieve, but we try to achieve one. Okay. This is the significance. So next two questions. These two questions, please. I see. No, it's a straight question, so um, it's not C. Please, question regarding assignment, I can't discuss it today because we are being mailed twice that some people, some peers are discussing assignment questions. So this would be kind of some measure, some strict measures can be taken against me if I do these things. So I can't discuss it today. I will definitely discuss it on the next day. In the previous year, these videos are being closely monitored by the NPTEL professors and professors associated on the team. So I can't please, means, I can't discuss. These questions are from the previous questions we can discuss, but the present questions we can't discuss. So please, please, I can't discuss it today. Okay, I'll definitely discuss it on the next. Fifth question. Fifth question. Anyone? Please. Fifth question. It is 1.38, right? 1.38, and percentage loss in wind turbines drivetrain. Sixth one. No, it's not 15%. It was in this week's lecture. Direct and submit. No, no, no. You can't submit late assignment. Whenever you have registered for the course, it's what it was clearly mentioned. Means you join the course late because you have a tentative deadline. I think the course joining last date was up to 31st August. So you can join up to 31st August, but course have started from 24th of July. So you need to, sorry, so 31st of July was the last date. So courses started from 24th of July. So you need to submit by 9. If you don't submit, you your no marks will be counted for the total marks that will be given as a part of your final certificate. So you need to submit it both the assignments. You need to go through the videos of 10 videos and need to submit by 9th itself. Otherwise, you that would be submission would be considered as incomplete. Okay. And six, no, no, not for 6D. Six is not D, not D, not C. 15 is also incorrect and 20 is also incorrect. So other out of the 5 and 10, the answer is yeah. So it is from directly from the lecture. Yes, it is 10. Yes, correct. It is 10. 7D, correct. 8, 8th one. Yes, it is lift and drag. It is lift and gas. Ninth one, tubular is used D or D. So uh, just give one answer because yes, D and D. Yes, 9D. D is correct because all these three types of towers are being used. It is from the lecture itself. Yes, 9D is correct. Okay. So 10th one. Yes, 10th one is C. Turns rotor and that is the aim of the geodrive. So here are some basic questions. So wind turbines are of some types. Yes. Yes. So what is the basis of these two types too? Yes, can you please just write in the chat box that why two means in which see what is this two coming from? Where is this two coming from? Means which two specifications are you considering so as to consider just to mention this as two? Yes, yes, correct. Vertical and horizontal. Thank you. So yes, variable pitch, constant pitch, these two. Mainly this question was framed based on the vertical and horizontal one. Yes, variable pitch, constant pitch is also correct answer. So second one, two second question. Uh, yes, yes, less than 1000 kilowatt. Third one, 3D. Anything else? PA. So A or D? A or D? You have the answer between A or D. It's uh, it's A. A is the correct answer because mm, yes, wind, wind anemometer means the information is being extracted from the anemometer. So A is the correct answer. Yeah. The fourth one. Yes, lesser. Lesser number of plates. More lesser number of plates, the operation will be smoother. Yes. So now just two, three questions more. One A. Peak speed ratio. Yes, it's correct. Mm, Two. Wind energy control system. Wind energy control system, conversion system, combined system, companion system. It's not correct. B is not correct. Yes, A is correct. A is correct. Question number three. 2B is not correct. 2A is correct. Wind energy conversion system is correct. 2, 3, C. Diffuse radiation. No, it's not correct. 3C is not correct. 3C is incorrect. 3B is also incorrect. So you are left out with A and D. D. So D is also incorrect. So the answer is A. Okay. So it is insulation. Insulation is the answer. So that's it for today. So if you have any queries, you can ask, or otherwise you can. Uh, on the next thing, I shall discuss the two assignments first, and then we shall have the week's overview and the two assignments we shall discuss. These are the previous year questions, and all these things are collected for us to discuss. No, it's I also thank you all for giving the valuable time in learning, because it's quite encouraging when some people at least interact or listen to what I say. Thank you, thank you very much. So on the next day we shall discuss, okay? And if somebody wants to join, the other session is being scheduled from 6 to 8. I think you have the mail, so you can join as per requirement if you think so. Okay. Thank you for giving your valuable time. Thanks. Smart. Okay, then. Smart.